Continuing on with question 4. This question is about mass on a spring. An object is placed on a frictionless surface and attached to a light horizontal spring. The other end of the spring is attached to a stationary point P. Air resistance is negligible. The equilibrium position is at O. The object is moved to a position Y and then released. Outline the conditions necessary for the object to execute simple harmonic motion. Well, there are two conditions that we need to remember. The first one is that the acceleration is proportional to displacement from equilibrium and the second one is that the accelerate and they're in opposite directions. So acceleration is in opposite direction to displacement. There's some variations on this answer that work. One is that you can say that the force is proportional to displacement. That's equivalent. And you can say that the force is in the opposite direction to displacement. Or you can say that the force is always towards equilibrium, which is equivalent to saying that it's in the opposite direction. Okay, next question. Alright, the sketch shows the displacement of the object from point O varies with time over 3 time periods. Label with the letter A a point at which the magnitude of the acceleration of the object is a maximum. Okay, so I'm going to predict that the answers are going to say any of the peaks or troughs here, but I'm going to choose a trough just in case, because at the trough the displacement is maximum and negative. That means the acceleration is going to be maximum and positive. And technically a positive number is bigger than a negative number, so this will be the maximum acceleration. Okay, label with the letter V a point at which the speed of the object is a maximum. So the speed of an object would be maximum there. That's also where it's maximum and positive, because the gradient is positive there. It's heading from the negative into the positive area. Okay. 3, sketch on the same axes a graph of, let me just check that question. Sketch on the same axis a graph of how the displacement varies with time if a small frictional force acts on the object. Okay, so we're starting at the same position. The first quarter of it is going to look very similar. So it's going to go through this point. But then it's going to start to lose energy and it's going to go through a slightly lower point. It's going to remain pretty much in phase with in fact, according to the IB curriculum, it's going to remain exactly in phase with the original one, but the amplitude is going to get progressively smaller and smaller. Like that. So we can go like this. Something like that. The end of my graph there didn't look very nice. Let's just fix that up a bit. Something like that. And continue on. So we lose energy with each cycle. Okay. This question is about standing waves. The diagram shows a tube that's open at both ends. Point A shows the position of one air molecule. A standing wave is set up in the tube. The graph shows the variation of displacement S with time for the molecule at point A. Okay. Outline whether a standing wave is transverse or longitudinal. Okay, it is outline here means that we need to say a little bit about it. So it's longitudinal. And that's it is a superposition of two sound waves which are longitudinal. Okay. The standing wave in the tube corresponds to the fourth harmonic. The speed of sound in the tube is 340 meters per second. Use the graph to determine the length of the tube. So we know V is equal to 340 meters per second. We know the first harmonic would fit a half wavelength. The second harmonic would fit one wave. The third harmonic would fit 1.5 waves. The fourth harmonic would fit 2 waves. So we can say fourth harmonic would fit. So where were we? It's a fourth harmonic, and we get 2 full waves. In the tube. So L of the tube is going to be equal to 2 lambda. So now the task remains to figure out what lambda is. So we know that V is equal to F lambda. We don't know the frequency, but we can use the graph to figure out the time period easily. And the time period is just the inverse of the frequency. So this is the same thing as lambda over the time period. So let's go back up and figure out what the time period is. So here we can see it's in milliseconds. And so one time period, this is one time period, and that looks like it is 1.3 milliseconds. From graph, t is equal to 1.3 times 10 to the negative 3 seconds. So v, or what we want is lambda really, yeah. So lambda is going to be equal to the speed of the wave times the time period, which is 340 times 1.3 times 10 to the negative 3, which is, using our calculator, 340 times 1.3 times 10 to the negative 3 gives us 0.442, so that's the wavelength. So 0.442 meters. But we said that the length is double that, because for the fourth harmonic, we're going to be able to fit 2 full waves into the pipe. And so L is going to be equal to 2 times 0.44, oops, not 8, 442, which is equal to 0.884. And we want that to 2 significant figures. So that's equal to 0.88 meters. Okay, the tube is now closed at one end and the first harmonic is sounded. Outline why the tube that is open at both ends produces a first harmonic with a wavelength shorter than the first harmonic of the tube that is closed at one end. Okay, so for a tube closed at one end, L is equal to, it's going to be a quarter of the first harmonic's wavelength, equals lambda 1 over 4. And then for a tube that is open at both ends, L is equal to We'll call that LC, and we'll call this one LO. L is equal to lambda 1 over 2. We'll call that lambda 1 closed, lambda 1 open. So you can see that lambda 1, so therefore, don't have much space left here, but we can say therefore lambda 1 C, let me just make some room for myself here. Well, because I'm writing with this big pen, I'm going to go outside the box, even though you're not allowed to do that. So we can say lambda 1 C is equal to 4L, whereas lambda 1 open is equal to 2L. So we can see that the one that's closed is going to have a longer wavelength than the one that's open. So we can say then lambda 1C is bigger than lambda 1 open, which is what we were trying to show.